Hi guys. So this is my follow-up video from the chi-square test for homogeneity setup. I'm now going to do a chi-squared test for homogeneity, an actual example. So hopefully some of the confusion and things we need clarification on from the setup can be a little bit more clear as I go through an example. So it gives you a little bit more concrete information on what exactly I'm talking about, because some pieces are a little bit tough to talk about in general, but once you do an example, they're a little bit more clear. So we have reports from 4 colleges on graduation activities of their 2006 graduating class. Are students' choices of post-grad activities the same across all colleges? So here's kind of what's going on. and the wording and structure behind this problem is a little bit weak. We would like a little bit more, which is going to cause a few issues throughout this example, but uh, we'll just go through this for the sake of seeing an example. So what we've done is we talked to 4 different types of colleges of students. So we talked to the agriculture students, we talked to the arts and sciences students, we talked to the engineering students, and we talked to the social science students. So we have 4 different samples and 4 different populations of kids we talked to. Okay, so these 4 different groups. And what we sought out is, okay, so after you graduate, what are you planning on doing? Are you going to go get a job and be employed? Are you going to go to grad school or some other option? So we have 4 samples, which is really coming from 4 populations, and we're checking, do each of these samples, does the breakdown match up for the 3 different categories? Does the distribution of people that went employed, grad school, and other, is that the same in agriculture as it is with arts and sciences, as it is with engineering, as it is with social sciences? That's what we're out to find out. Okay, so we're going to start off with our null and alternative hypothesis, because remember, we don't have a parameter here. For our null hypothesis, if you go back to when we did the setup video, what we're going to look for is we're going to say, and we're going to assume the distribution of these different activities is the same. So the distribution of post-grad activities is the same across all colleges. So these 4 different groups that we talked to. That's what we're going to assume is true. We're going to assume these distributions, these breakdowns, are in fact the same. What we're seeking to prove in our alternative hypothesis is the distribution of post-grad activities is going to be different. And that's different across all colleges. So it's different across the agriculture to the arts and sciences to the engineering to the social science. So we're getting to our assumptions, and because of the lack of structure on this problem, we're going to run into a few issues, but we'll just talk about what we want, and we'll just proceed onward. So our assumptions, the first one that we need to check is you want randomization, and we can also talk about the second one is 10%. So what you're really wanting is across everywhere that you collected a sample from a population, you want each of those individually to be randomized and each of those individually to be less than 10% of the population. So we hope that this group of agriculture students, the 669 we talked to, we hope these guys were randomly selected in less than 10% of the population. The arts and sciences, we hope this 666 is randomized in less than 10%. These 482 randomized less than 10%. The 279, again, randomized in less than 10%. There is no information in this problem whether we collected that information or not. But it is pretty safe to assume that of all agriculture students across all colleges, we hope 669 is less than 10% of all agriculture students in college. So can't really do much with the randomization. We can do some things with the 10%. So we hope all 4 samples were randomly selected. So to make this problem better, you maybe put a piece in there that says the students from each college were randomly selected. That would help achieve that. each sample is less than 10% of the population, which that's good for us as well. This third one is going to be the one that's going to require quite a bit of work, but thank goodness for calculators are going to help us out. So what we hope is all the expected counts are at least 5. Now this is something that you need to know how to calculate on your own. Calculator, yes, it can do it, but it's something you still need to know how to do yourself, but it's going to help us out here. So here's how you calculate expected counts. So this particular problem, the data we're really interested in is just the agriculture to social science. So we don't care about the total column there. And then from employed down to other. So again, we don't care about total. So we care about these numbers right inside here. So what we need to do is we need to calculate the expected number of students we expect to have from the agriculture school that are employed. We need to calculate the expected number of arts and sciences students that are employed, engineering employed, social science employed. Same thing, agriculture and grad school, arts and sciences grad school, so on and so forth. And then finally, agricultural other, so on and so forth. So there's a total of 12 expected values that we have to calculate. Here's how you're going to do that. You're going to take the row total times the column total and divide by the table total. So the row total times the column total and divide by the table total. So if I wanted to calculate the agriculture employed expected count, I'm going to take the row total, which is 1052, times the column total, which is 669, and we're going to divide by the table total, which is 2096. That calculation right there would give you the expected count of this single cell. The row total, 1052, times the column total divided by the table total. Okay, so we would type that in the calculator, get our expected count there. Now I'm going to hold off on a second because I'm going to show you a way here in a little bit that helps speed this up. But again, this is a calculation that you need to know how to do. I'll use a different color here. So if I moved on to the next cell here, the arts and sciences and the employed cell. So I want to calculate the expected count here. We have to take the row total, which is 1052, multiply by the column total, which is 666, and divide by the table total, which is 2096. Okay, so you'd have to do that for this cell. Then you'd have to do it again for engineering, and then here, and then the next row. Okay, so just another example. If I want to figure out the total or the expected count for this guy here, so engineering and other, the row total would be 322 times the column total, which is 482, and divide it by 2096. Okay, row total, column total multiplied together, divided by the table total. So if I'm doing this by hand, that's a lot of expected counts that I'm going to have to produce on my own. Thankful for us is we do have the power of calculators. Okay, so I'm going to kind of skip ahead and jump around here, and it seems like, well, can you actually do this problem yet? I hope so, but I'm going to set some things up in my calculator to help me out with this whole process. So if you bring your calculator in front of you, let's go ahead and peek at where is this test actually done in our calculator, and it's going to help us construct and do this. So if you go to Stat, go over to Tests, you're going to scroll down. You will see your 2 chi-squared tests listed in the calculator. We have 3 total, but there's 2 listed in the calculator. We have a chi-squared GOF test. That's the goodness of fit test. So goodness of fit has its own option in the calculator. Then option C is what we want here. It just says chi-squared test. We're going to use this guy for homogeneity, which is what I'm doing right now, and independence, which we'll do later. It's going to ask you for a few things. It's going to ask for the observed values, the expected values, and you're going to calculate. What these are right here is these are matrices, okay? So these are matrices. Basically what we want to do is this red bracket that I created here, we want to put all of this data into the calculator. So we can't exactly do that by doing stat edit. we need to put it into a matrix. So here's how you're going to accomplish that in the calculator. Over here to the side, we have an option that says matrix here. So we can get out of that for now. We don't need it. I just want to give my calculator information. So we're going to do second matrix. And what it's going to do is it's going to list out, hey, here's all the matrices you can have in your calculator, but I want to edit a matrix. So we're going to slide over to edit, and I want to edit a matrix A. So what you need to do, if you're not familiar with matrices, is you're going to put the number of rows first. So we had 3 rows, employed, grad school, and other. And then we had 4 columns, agriculture, arts and science, engineering, social science. So I did 3 by 4. Once you hit enter there, it's going to jump down, and you can just start typing in all your numbers. So I already did this to try and save me some time here. 379, 305, 243, 125. Okay, then you jump down to the next row. 186, 238, etc., right? So when we peeked at the chi-squared test, it wanted 2 things. It wanted the observed counts and the expected counts. You do not actually need to do the expected counts. So I have filled in observed. I'm going to run this test. Okay, what the calculator is going to do is it's going to go ahead and do all the calculations for you for the expected counts, and it's going to plug them all in for you in matrix B. So it's going to do a lot of this work for you. It's going to create matrix B so that it can actually carry out this test. So I'm going to say, hey, go ahead and calculate this, and it spits everything out. It just gave me a chi-squared test statistic. It gave me a p-value. It also gave me degrees of freedom. It just did everything that quickly. But where I'm at on my paper is I need to know what my expected counts are. So if you go back to second matrix, you might not have noticed earlier, but there was, I believe, a 1 by 1 matrix here. It automatically changed it to a 3 by 4. So if you go down and highlight matrix B and hit enter, what it's going to do is it's going to show you all the expected counts for matrix B. Okay, it's going to show you all of them. So what it did for us is it took the row total times the column total and divided by the table total. It did all of those calculations for us. Now, what would we need to do on one of these problems is we do need to show this. Again, even if the calculator did these calculations, you need to know how to do these calculations yourself. Don't entirely depend on the calculator. What I'm going to do is I'm going to copy down this information just in a tiny little corner over here, and I'm going to round them a little bit because we do need to show what the expecteds are. So I'm going to have 335.7, let's do 78, 230.45, 102.78. In my next column, 334.27, 229.41, 102.31. Oh, it jumped over. I went too far. Or did I copy? Did I skip? What have we done here? I might have skipped a column here, or we have a lot of repetition. One, two. What am I missing? I think I'm at 140.03. No, this is the final column. So it jumped around. It's kind of being a pain right now. 96.10, 42.86. I'll go back and get this one. There it is. 241.91, 166.03, 74.05 there. A little bit messy there, but we did get them all down. So, have all my expected counts. We needed to make sure they were all at least 5, which they are. So all expected counts are at least 5. So because of this, we can now carry out the chi-squared test for homogeneity. So when we jump down to our formula, all we have to show is we have to show just a little bit of it that we know what we're talking about. So for the chi-squared, remember the formula is the summation of observed minus expected square divided by expected. So working our way through, and we're going to use our expected counts here. The observed value, I'm going to start with this first cell, 379 minus my expected of 335.78. We're going to square it and divide by 335.78. The next cell, you would have 305 minus 334.27. Square it. So I'm taking the corresponding cells in each of my observed matrix and my expected matrix. 305 minus 334.27. Square it. Divided by 334.27. Now, if I was writing this all out, I'm going to have to write out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 calculations there, which is a lot of writing. I've demonstrated at this point that I know what I'm doing, so I'm going to do a plus dot dot dot, and then I'm going to let my calculator take over the rest of the work from there. So scrolling down back to my chi-squared. My test statistic here, it used matrix A, the observed values, the expected values. It came up with 54.51. Okay. Another thing that we're going to need here is with chi-squared, we're going to need degrees of freedom, which what we're going to take is the number of rows, which is 1, 2, 3 rows, and subtract 1. So we're going to take 3 minus 1 and multiply it by the number of columns minus 1. So 1, 2, 3, 4 columns minus 1. So the number of rows, subtract 1. The number of columns, subtract 1. Notice I did not count the total columns. These are useful for calculating expected counts, but they have nothing to do with really an actual data set. This isn't another sample. This isn't another sample, and this isn't another category. So all I care about is the information in here, the actual data, not the totals. So if you take 3 minus 1 times 4 minus 1, what you're going to get is a degrees of freedom of 6. So if you go the route of using the table, you can do that. Remember in my intro video to all chi-squared, typically, if these are close, you know things are pretty good. We're very, very far apart. So for my chi-squared distribution, with a degrees of freedom of 6, the center or average of this distribution is going to match up with the degrees of freedom and also be 6. So if the center of this is at 6 and we have a chi-squared test statistic of 54.51, we are very, 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 very far away from the center of this, which kind of hints at what's about to come. So I'm going to go way over here and say 54.51. Our p-value, remember, is always the area to the right, so probably that chi-squared is greater than or equal to 54.51. Our calculator spit out something that was pretty interesting there. It said 5.819, blah, 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 e to the negative 10. This is how calculators show scientific notation. This is 5.82 times 10 to the negative 10. So really what we have here is 9 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 5, 8, 2. That is our p-value, okay? Incredibly, incredibly small. So pretty much every alpha out there at this point that we typically use is going to lead to the same conclusion. So we are going to reject the null hypothesis. The reason for that is our p-value is less than, and it didn't designate an alpha, but I'm going to use alpha p equals 0.05 level. And if we're going to reject the null hypothesis, that means we have sufficient evidence to say, and we're just going to state our alternative hypothesis again, sufficient evidence to say the distribution of post-grad activities is different across all colleges. So essentially, what does that mean? It means, agriculture kids, they kind of are doing one thing, employed grad school or other. Arts and sciences, they're doing their thing, employed grad school and other. What it's saying and what we proved here is not all four of these colleges are doing the exact same thing. Their distributions are not the same. So we're not matching up that the proportion of the folks going to employed, the proportion of folks going to grad school and other, it's not relatively the same across all four colleges. It is different. That is what we just proved. So that is my chi-square test for homogeneity. Yes, it's quite long, but fairly straightforward if you've been keeping up with all of your hypothesis tests. Thanks.